Hello, everyone.
Awesome.
Welcome to the afternoon session. We have the pleasure of having Prineha and Narang from UCLA talk about probing carrier interactions in quantum matter using electron hydrodynamics.
Awesome. Thank you so much to the organizers for having me here. It's really a privilege to be at this wonderful campus and see so many folks here that I've followed and work that I've admired over the years. So I had this moment of what do I talk about at this conference? I could talk about open quantum systems. I figured after all the talks here, you probably don't want to see Lindblad one more time. Then I thought to myself, I could talk about driving quantum matter optically. That might be a little more relevant for experimentalists. I looked around, realized there are 0 experimentalists in the audience. So I figured I'd talk about something that has been my recent obsession, which is thinking about electron hydrodynamics, particularly how electron hydrodynamics could tell us something about quantum matter that we would not learn in other regimes. So before I dive into the science, I want to acknowledge the folks who've actually done the work. A lot of the work I'm going to show today was work by one of my former students, now Miller Fellow, George Varnavides, as well as a Simons Fellow, Adam Germain. They've worked together on this topic with me for many years. A postdoc who's now Yashin Wang, she's on the faculty at IOP in China, as well as a whole host of experimental collaborators. So I want to convince you that this lens, this idea of thinking about hydrodynamics actually is complementary to all the other ways that we think about quantum matter, and in fact could tell us something that we would not learn in other ways. But before I convince you of all of that, I need to tell you a little bit about what is electron hydrodynamics and how we've started to think about it. So hydrodynamics effectively is a theory of conserved quantities. And we tend to think of this as something that's happening in an interacting fluid. And note that at this point, I haven't specified anything about what type of fluid. And that's something that has become quite interesting in some of these systems, because of course, we can say it's all just electron hydrodynamics, but there are some intriguing results that show that perhaps you could even think of it as an electron phonon fluid. But getting ahead of myself, let me continue to tell you a little bit just what is conventional electron hydrodynamics. So typically you'd say, okay, well, as soon as I have this conserved quantity, maybe I'm in this semi-classical regime, right? It all just becomes something that is semi-classical. Well, sort of. Ultimately, we're dealing with things that are many body. We're interested in things that are inherently quantum mechanical, though yes, eventually, if you invoke hydrodynamics in the sense of this conserved quantity, you could say perhaps we're semi-classical. This is another debate that comes up a fair bit, how semi-classical, how quantum mechanical, and how do these regimes differ. Okay, so it's important. And I think that the fundamental importance here for this audience is perhaps much more relevant than talking about the technological importance, in part because it gives us this way of thinking about condensed matter differently. But there are also a whole bunch of questions that come from hydrodynamics in non-quantum systems that we could think about as being realized here. So types of pre-turbulent and eventually turbulent regimes that are hard to study in real hydrodynamics. Perhaps we could think about the energy cascades and the Euler singularities as well, associated with what we can observe here in quantum matter. One of my colleagues, and of course celebrated mathematician Terence Tao, has talked about this extensively. And the question that really he's posed in the past is, can you make water explode? That essentially is how he thinks about some of the energy cascades associated with classical hydrodynamics. Now, we're a long ways from thinking about some of those very exotic regimes with electron hydrodynamics, but I want you to keep in mind that it's not just a one-way street of us trying to map all of these ideas from classical hydrodynamics to quantum matter, but perhaps we could also go in the other direction and learn something about those regimes. If you're interested in how this is relevant technologically, well, we can make interesting devices. The hope is that eventually some of these would also be very low dissipation, and that might help a fair bit in interconnects. Okay, so formally, what do I mean by electron hydrodynamics, and how can I I say for sure that I have something that is in this regime? I'll stay here, but I'll start with it so we can get this out of the way. And I'd say electron hydrodynamics is observed when there's some microscopic scatter time and length scales, okay? And these time and length scales need to be large compared to that of the experimental. Anything about boundary conditions without saying something about the genre of device you're making is not particularly relevant. So with all of that, if you can satisfy all of these conditions, and we'll unpack how you might actually go about establishing these in specific types of quantum matter. I don't know what happened here, so maybe does someone want to help me? This was fine a second ago. Okay, all right. Well, I'll just keep going. Okay, so when we think about all of these conditions that need to be satisfied, from a theory standpoint, we need to actually be able to calculate some of these microscopic scattering processes. Then we need to establish over a large length scale what these look like, and then think about eventually how these compare to that of our geometry, experimental probes, some kind of boundary conditions. And we'll probably debate those boundary conditions quite extensively as we go along. The simplest thing for students in the audience, you might be familiar with this. When we have electrons, they're flowing. Typically, you talk about ballistic flow. It's the simplest thing you can do. This is where perhaps you can invoke this ultra clean limit. And this is simply a special case of the Boltzmann Transport equation. Now, something that I will build towards, and I've so far swept under the rug here, is I've talked about these electron fluids in very hydrodynamic language. You might say, well, ought to be talking about Navier-Stokes, and suddenly I've told you we have Boltzmann Transport. But really, what we think about when we are dealing with transport with electrons is the Boltzmann Transport equation. And I need to build up towards telling you that these two things are not entirely different, though just thinking about a viscosity or just thinking about Navier-Stokes may not be sufficient for us to arrive at the same conclusion. But let's build up towards that. Okay, so ballistic flow, simply a special case of the Boltzmann Transport equation, no problem. Diffusive flow, again, something that we know pretty well. You have impurities, you have some edges. Again, you can get this very easily from the Boltzmann Transport equation. And eventually, in the case of diffusive flow in particular, you talk about a mean free path. I'm going to use the word mean free path and lifetime somewhat interchangeably. And hopefully you'll forgive me for that, particularly if you do a lot of transport measurements where only one is easy to get. Okay, but hydrodynamics is essentially a limiting case of the Boltzmann Transport equation. And this is where we're talking about things with strong interactions that give us this kind of a viscous flow. And ultimately, this is something that shows up in the spatial profile, okay? And that's important because this is back to that point of there being something about the experimental probe that'll be imprinted, right? This would look very different if instead of this little defect here or this circle that I've drawn, if I had a different geometry of how this fluid ought to flow around it. And this is intuitive for us. We're used to kind of thinking about this. We're not used to thinking about this when we take a limiting case of the Boltzmann Transport equation. So our first task here was to actually think about from Boltzmann Transport equation with all of this spatial information retained, how do we actually recover this hydrodynamic regime? Will I see that same spatial profile if all I put in is the type of material I have, all the electron-phonon interactions, perhaps I get very ambitious, have all the phonon-phonon cases, I put all of that into Boltzmann Transport equation, do this over a large length scale, will I get that nice spatial profile, right? And how would I know, particularly because most Boltzmann Transport equations out there throw away a lot of that spatial information, and many of them actually invoke the relaxation time approximation, which I'll show you here is not actually a good approximation to make. So let me tell you a little bit about that and the different transport regimes we find, and then build up towards the Navier-Stokes component. And if time allows, I'll also tell you how sensitive we are really to all of the scattering details. So really, how much of that microscopic information do I need to keep versus how much of it is nice to have? Okay, So with Boltzmann Transport, we're familiar with this. Essentially, it is a semi-classical equation. We're working with a one-body distribution function here, and we can specify the reason it becomes a semi-classical equation here is because we are specifying the positions and we're thinking about a quasi-momentum, right? So we're thinking about something that looks as though you have a bunch of particles going into this high-dimensional space, and I can write out two operators, specifically a streaming operator, which, as the name suggests, is the set of things that stream through without any collisions, and the collision operator. And this is kind of the simplest version of writing out this BTE that we can do. So of course, now we introduce the electron interactions, and it's very easy to say that, well, as soon as I have phonons, I ought to just bin those things in the collision term. Maybe that's all the stuff that actually will relax momentum. And I say, well, not so fast. Turns out there are a couple of intriguing things that happen here. So the momentum relaxing terms, and I'm just going to call this tau MR to avoid stumbling over this for the next n minutes, are easy to identify. Anything that has an impurity probably will relax momentum. It's going to scramble stuff. Stuff will interact. It will not go the direction it was in that nice flow profile that we were interested in. And then there's a bunch of stuff that will conserve momentum. In terms of those momentum conserving interactions, again, you can think of the Coulomb interaction, you can think about a phonon mediated electron-electron interaction. There's a whole set of diagrams you could write out that correspond to these. Something we've done a fair bit of in my group is actually evaluate these at finite temperature, as well as evaluate them beyond leading order. I'm not going to give you the gory details of all the methods we've developed. However, I am here for the next few days, so if you're interested, I can show you some of those methods, and better yet, get you going on those methods if you're so inclined. Okay. But in the presence of strong interactions, we can say that, okay, regardless of what gives us momentum conservation, things look like molecules in a fluid, and they're conserving momentum, and they're flowing a certain way. With all of that, what I can do is actually write out a set of invariants, and I'm spending a little bit of time on this because the rest of the talk otherwise ends up making very little sense. So these invariants are carrier number, energy, and thinking about total momentum. And this is where it becomes clear that the relaxation time approximation will not work for us. This is something that shows up all the time in all the transport methods. If you take something off the shelf, the first thing that shows up is this is within RTA. Right? If you've seen within RTA, it's not going to work for hydrodynamics. It doesn't conserve any of the invariants we're interested in, so bad idea. Okay, but maybe I can go a little bit beyond that. And yes, the Lorentz diffusion model has been around for quite some time, conserves carrier number. Remember, that's not sufficient for us to talk about hydrodynamics yet. So the next more sophisticated thing I can do is the so-called Callaway's hydrodynamic model. It has tau MR, tau MC. I can weight that one-body distribution function. It conserves the carrier number and the momentum. We can actually parameterize this. And now what I can simply say, if I didn't want to do all the BTE calculations, is that I can use this model. I can bin these numbers in this MRMC category. Doesn't matter how I get them, and be able to populate something that looks like a nice transport regime diagram. And that should, at least to leading order, tell me whether or not I expect hydrodynamics in a particular system, right? So there's a system where, say, MR, it will always wash out MC. Doesn't matter if I make it ultra clean. Doesn't matter if I get it to some exotic regime. If that's the case, maybe that's not the system I look at for hydrodynamics. Maybe there's another material where I can more easily or more readily realize this particular regime. Okay. So we went ahead and did that, and let me just tell you a little bit about what this would look like with that experimental probe component incorporated, right? So I've told you the microscopic details, a little bit of how you would treat the transport very simply. Haven't shown you the full spatially resolved BTE yet, but the one thing that is super important here is the fact that almost everyone in the field who's looking for hydrodynamics patterns some form of channel, right? And this could be as you think water in a pipe. Well, the direct analog of that would be for some channel to be patterned in a transport device to allow there to be, say, some flow. And what I'm going to be looking at here is the current density relative to this channel width, right? I can change the width of this channel. Don't think about complicated scenarios with two channels, things entering, flowing out, all of that, too complicated for us. Just the simplest thing we can do is look at this current density profile. Okay, so with that, what you would expect in the hydrodynamic limit is this very nice puzzled flow, this super bendy profile. This should look like a nice smoking gun signature. Should be really, really easy to identify, right? Well, let's see what we're comparing it with before we say it's going to be really easy to identify. The other things we're going to be looking for, and by the way, those MR, MC will now be weighted by the channel width. Again, this is that experimental probe entering our calculation. Okay, but the diffusive regime will not just be diffusive. There'll be a quasi-diffusive regime, again, depending on whether MC or MR are much larger than or much smaller than the channel width, right? Condensed matter is never quite as simple as I have a smoking gun signature, I go find it. If that were the case, I'd be an AMO physicist, life would be a lot easier. Unfortunately, it's not. So I have a quasi-diffusive, a quasi-ballistic, and a quasi-hydrodynamic regime, and they all look roughly very, very, very similar, right? And this is where identifying hydrodynamics in this pattern channel type geometry has been so challenging for folks, because the quasi-diffusive looks like this flat top with these kind of drop-offs that are right near the edges. The ballistic kind of looks a little more curved, and then the quasi-hydrodynamic, of course, looks like the parabolic flow that we expect to see. Okay, so with all of that, what I can do is say, well, I don't just have these extremes, maybe I can populate a whole transport regime diagram. Not quite a phase diagram, by the way, but again, something that we're going to move around in this diagram using temperatures. We could take temperature trajectories through it. And to start, let's just solve that simple Callaway's hydrodynamic model on a grid of these pairs that are normalized by the channel width. If I go ahead and do that, and I can now look for the curvature, right? So what are things like in the middle of the channel? That's a good way to characterize this. So I have momentum conserving interactions here on the x-axis, the momentum relaxing on the y. This is a log-log scale going from weak to strong, again, going from weak to strong. And the color here represents the curvature, okay? So remember on the previous slide, I showed you essentially those three regimes are characterized by the type of curvature they have, what the current density profile looks like. Okay, so in this scenario, quasi-hydrodynamic is going to sit here on the top left, quasi-ballistic top right, and quasi-diffusive somewhere down here. And you'd say, okay, great. This should be straightforward. We're going to be able to be on the top left of this diagram and find this regime, and that'll be great. I haven't even gotten to this point yet, but I'll just give you this part of the story beforehand. Most of the experiments, whether it's graphene, some of the vial semi-metal work, some of the other systems that we've looked at that are just semi-metals, kind of falls somewhere around here. So it's maximally confusing to be able to attribute that curvature to being hydrodynamic. There's a little more that you need to be able to do. But the good thing is that we can move around in this diagram and take kind of temperature profiles through it. So you can think of going from one regime to another and looking at what that curvature trajectory looks like. And that ought to be able to say, aha, I've gone from a hydrodynamic to ballistic regime, or a hydrodynamic to a diffusive regime, and things of that nature. Okay, so with all of that, I want to tell you how would we actually look for this current density curvature? How would we actually look for this signature experimentally? And our technique of choice, these are collaboration with Amir Yacobi's group, has been to use NV center magnetometry. The short version of it is that this is an amazing way to map out what that current density profile looks like. Technically, you're looking at the induced magnetic field rather than actually looking at the current, but that's a little detail here that we're going to sweep under the rug. And essentially, you can kind of scan this. The key insight from Amir's group has been not only to develop this technique, but also develop this technique in a way that you can do scanning and variable temperature. So you can kind of go from a particular temperature to another seamlessly, and of course, be able to look at these types of devices, not just graphene, but also other systems where, say, a 3D crystal, where you could actually pattern into a good transport axis. And that's important because it was believed that all of this is just graphene, and the type of hydrodynamics I'm talking about that I'm particularly interested in is hydrodynamics beyond graphene. Okay, so you've seen the results in graphene. It's fairly straightforward to see that. And it's easy to establish that it's not the same as transport in other systems like palladium. Of course, if palladium here looked hydrodynamic to us, we would have some issue because we don't expect it to be hydrodynamic. We expect very, very boring diffusive flow in this system, right? With all of that, the system that we have been very interested in is Tungsten Telluride. Let me tell you about this system. It's a very rich system, and I could give a whole talk on it. I won't. I'll give you the TLDR. It's about semi-metal in certain cases, a trivial semi-metal in certain others. And again, Depending on the amount of strain, people talk about whether it's type 1 or type 2. It's a layered system. So like graphene, you could exfoliate it. And of course, the types of samples we're interested in are multi-layer, ones where we could ask the question whether or not the topologically trivial or the topologically non-trivial phase ought to be hydrodynamic. Right? We thought that was a fun question to ask. Again, this is hydrodynamics beyond graphene. So it's also interesting to ask what is the origin of hydrodynamics in this system. Okay. For us, we went about predicting all of those momentum conserving, momentum relaxing interactions in the system from first principles. And that was relevant in part because this is a scenario where we first predicted and then it was experimentally realized, order matters, that this system ought to have not only well-defined hydrodynamics in the non-vial phase of it, but also a key prediction of the theory was what temperature would you expect there to be peak hydrodynamics, right? Remember that current density curvature, sure, you could look at it just the right way and claim it's hydrodynamic, but it would be really hard to say that there's a particular temperature at which we expect this curvature to be the largest, and that's exactly what we did. Down here, showing you the predictions, and hopefully folks can see this from on the back. But if you can't, really the point is that this is the channel now. And we're looking at the induced magnetic fields. Again, remember NV magnetometry technically measures induced magnetic fields, not directly the current density, but we can reconstruct from that. And we can, of course, scan over different temperatures. The temperatures that are relevant are roughly 15 to 20 Kelvin. That was around where we predicted peak hydrodynamics, and that's where it was measured experimentally as well. And some of the other things that we were able to predict about the system, which are actually the most interesting thing here, is that it's the phonon-mediated diagram that is responsible for hydrodynamics in tungsten telluride, not the conventional Coulomb interaction. And this was interesting because that makes it quite different from graphene, but also there's a whole bunch of other systems that have the same phonon-mediated diagram that appears to dominate. Some of those systems include things like tungsten phosphide, which is about semi-metal, and also a system that we've written a fair bit about, and slightly newer systems like palladium cobalt oxide, zirconium silicon sulfide, tantalum arsenide. There's a whole bunch of these, both trivial and non-trivial semi-metals that people have made and claim that there are signatures of hydrodynamics. So far, things I've established are what is origin? It's phonon-mediated. I've hopefully convinced you that we can actually look at the spatial signatures. What I haven't convinced you of is that this is general, right? This applies to lots of systems, and perhaps there are even design principles to be gleaned from the system. Okay, so tungsten telluride is very, very special. People can make ultra pure single crystal samples of this with very, very long mean free paths. That's exciting. These are samples from Claudia Felser's group, but that's not always the case with every system. So in tungsten telluride, we could very easily identify what is this temperature trajectory that we're taking through this transport phase diagram, or regime diagram, sorry, and really overlay the experimental observations. These are the blue points with the various trajectories that we were interested in. But how about we pick a system that is a little weirder? Okay, so I'm going to show you examples of systems where we try and establish that this mechanism is general. And tell you why we think it's general. Okay, so there are, empirically, if you think about this, a lot of systems where there's this shorter phonon-mediated electron time, right? So what would we really need to establish? We need to establish that this normal electron phonon line width, the thing that everyone really struggles to calculate at finite temperatures, is actually the one that is being washed out or dominated by this phonon-mediated electron-electron line width, right? And you could always think of it as there'll be temperature regimes where one dominates over the other, perhaps looking at the functional form ought to be sufficient, but there are a few things about this that are actually tricky. One of these is that you need to be able to do the sum explicitly over the entire Brion zone. Fine, figure that out, no problem. But you also need to be able to do this at finite temperature, including really low temperatures. And turns out that that's more than just a technical challenge. Sampling this very heavily at lower temperatures, particularly temperatures that are, people always ask me, can you do this at millikelvin? And I tell them, this is not the type of calculation that's easy to do at millikelvin. This is the type of calculation that's easier to do at 10 Kelvin. But with all of that, we kind of looked at this and looked at the functional form, took a few limits, and realized that yes, in fact, the design principles we're looking for are there, and there are some interesting things we can say about it. First is that many of the approximations that we're looking at are actually going to be valid for many materials that are in their non-superconducting state. So even though tungsten telluride at very low temperatures is an interesting superconductor, that's not the regime that we're interested in. Slightly higher temperature would be good. The mechanism will always rely on this virtual phonon exchange. So we want to be at temperatures below the Debye temperature. And then, of course, there's some things that we can do that are conventional Fermi surface analysis. So looking at something that has the pockets are separated, there's some low symmetry. And if you can satisfy all of these things, life ought to be good. A prototypical example of this is palladium cobalt oxide, and the reports of looking at hydrodynamics kind of going both ways from the resident group and a few others. And what we realized is that something that all of our previous calculations were missing is the richness of the Fermi surface incorporated into that transport calculation. So this is yet another thing where kind of thinking about the faceted Fermi surface and then how the transport axis is aligned relative to that Fermi surface ought to be important. So a good example of that is palladium cobalt oxide. Let's talk about that for a second. It's a nice single band metal. It satisfies all of those criteria that I put forward in our design principles. You can make even larger impurity mean free paths. So this is a very, very ultra clean sample. Tens of microns ought to be able to make a really, really large device out of it. And the photon mediated interaction dominates over a large temperature range, right? Seems like an easy system to observe hydrodynamics. Not so fast. So it turns out that because it has this nice faceted hexagonal Fermi surface, thinking about how the transport is aligned relative to it tends to dominate the rest of the signature. So if we look at something that is perfectly aligned with the Fermi surface, the overlay points here would essentially be the ones that you find in a temperature trajectory through palladium cobalt oxide, right? But that's not always the case. If things are misaligned, turns out that you would actually see something very confusing. And I'm talking about Neumann's principle here, but I'm actually going to get to that in the next few slides. Okay, so it has directions that allow for easy and hard transport. And I can see that if I look at something that's completely aligned and then maybe something that has a 30-degree rotation, and I look at a difference between those two transport regime diagrams, it would look as so. And you'd see actually that the curvature and the debates that people had around whether or not this is hydrodynamic at the temperatures that they were looking at, whether it's all ballistic flow, can be reconciled just by knowing something about that set of axes. Okay, so won't spend too much more time on it. I see I have about 9 minutes left. So next I want to tell you about how we would think about this from a Navier-Stokes picture, and whether or not that's appropriate, or what you would do in the context of Navier-Stokes to make it more appropriate to look at actually anisotropic materials. Okay, so let me tell you about that in the next few slides. Okay, so if you're like me and had not seen the Navier-Stokes equation since you took graduate version of it, let me just run through it very quickly. There's a mass conservation equation, a momentum conservation equation. It has an advection and a fluid stress term. And this is very, very general, by the way. This doesn't matter what kind of fluid you have. As soon as you have Navier-Stokes, you can write these down. And then you have some version of viscosity that you write out. And this is where rubber really hits the road, because this viscosity here is a nice rank 4 tensor that we're interested in, not to be confused with a number for the viscosity that has been assumed quite frequently in condensed matter. And this is, I say rubber hits the road because that's where all the rich physics lies. Okay. So classically, this viscosity would relate the stress to gradient in our fluid velocity. And if we have rotational invariance, which we do in water and other kinds of fluids, life gets actually quite easier. You can just talk about the scalar or shear viscosity. Remember, crystals are different. Real materials and condensed matter is rich, and that's my way of saying it's complicated. It's complicated because the viscosity is really only constrained by the symmetry of the point group of the crystal, and that's really it. So if you try and throw away the rest of it, you're throwing away actual information that is contained in the viscosity tensor. And we know this as Neumann's principle, that the symmetry elements of any physical property of a crystal must include the symmetry elements of the point group of the crystal. And what that really does is breaks up this viscosity tensor into 3 identifiable components. An anisotropic behavior, this is, as the name indicates, the one that will encode how much anisotropy we have, a dissipationless Hall behavior, as well as the vorticity behavior of this viscosity. And we can kind of identify and look at these explicitly. Okay, so we went ahead and did that, and won't bore you too much with a lot of group theory this afternoon, but just to say that I can impose the different symmetries, and I can look at what type of tensor I have and how many independent components of that viscosity I ought to have. And this is, again, key, because then you'd actually have, or you could propose experiments to look at these independent components of the viscosity, right? And this is slightly different from what you expect. With graphene, people got really lucky. It's very symmetric. So it turns out that everything collapses down to a viscosity number. With all of these other systems, particularly these low symmetry valence semi-metals that we've been looking at, turns out that throwing away all of that information is really not viable, because the number of independent components you have is actually quite large. So with that, what we can do is kind of identify for the dissipative Hall or the vorticity coupling what the independent components are, and how we go about looking at them. Okay, so instead of doing this with numbers, maybe we could just do this using colors. Okay, so I'm going to encode the dissipative in blue, Hall in red, and vorticity in this purple color here. I realize now that if you're colorblind, this color scheme will not work all that well, but just try and follow along with the words here. So the most general tensor will have kind of all of these components. But of course, looking at something with fourfold C4 symmetry, I can constrain this and get this fourfold rotated viscosity tensor. I can similarly do a few more transformations and get to D4 and identify which of the components of it are dissipative. I can similarly kind of get fancier with this and figure out what's going to happen with something that, okay, I'm not going to belabor this point. Okay, so with all of that, what's an observable, right? So these ought to show up in experiments, and the first thing that you'd want to see is something that shows up in a Corbino disk type geometry. This is a very common thing to do for classical fluids, and we figured why not for some for electron fluids as well. Turns out people can actually do these Corbino disk geometry measurements. Okay, so for SO2, stream plot, very simple. D4, you should start to see some of these wiggles. And then if you look at the difference, you should actually start to see some of these steady state vortices. Okay, that's fine. I think these steady state vortices should be identifiable, but that's still just the anisotropic component. If I look at the dissipationless Hall viscosity here, not going to show up in that Corbino disk, so you'd have to actually think of a different type of geometry here. Turns out that these kinds of pressure drop measurements are things that people also do in classical fluids. We figured why not propose a voltage drop version of that, and that ought to show you some interesting behavior as well. And here you'd actually be looking at a pressure plot. You're looking at D2H minus C2V. Those are two pretty common symmetries, again, to compare what would show up here in the pressure plot. This is all to say that the spatial signatures of transport that people would measure here ought to very easily show us some of these unusual or anomalous parts of the viscosity tensor. These are not as hard to get at as originally thought. Same for the vorticity coupling, right? So you can imagine now creating a constriction and flowing things in. And imagination is really the limit here. Why a single constriction? Why not a second one? Turns out you can actually have something similar to a 4-point probe measurement here, but 4 constrictions coming in, and you ought to even be able to create some interesting, not just vortices, but also pre-turbulent regimes somewhere in this fluid by crossing the flow coming from opposite ports. Again, this is all to say that the different parts of the viscosity tensor give you access to physics you would not have, again, if you'd thrown away some of that information. Okay, so to do all of this, we introduced a method, and I'll just give you 30 seconds on this, called Spartans. This is a name picked by George. So it was to recognize how epic this problem is. And the thinking is that to be able to do this entire problem, keep all the spatial information, go beyond RTA, we ought to do some tricks here. One of the things we've been able to do, and let me just jump right to it, is split the part of the problem that deals with the geometry from the part of the problem that does the transport, from the part of the problem that does the microscopics, and bring it all together. Okay. So all of those nice diagrams that we looked at, all the microscopics, finite temperature, we can kind of deal with that separately, bring all of that into this method. And then essentially what we can do is have some source term, have some way of introducing where the carriers are starting out. We can discretize the geometry. It doesn't have to be very symmetric, doesn't have to be 2D. And all these things I've shown you, you might think I can only do a 2D problem. That is not the case. We make the weirdest possible geometry, and we can actually deal with that. And it's massively parallel, also something that is important. And this is something that we've shown not only on the Summit supercomputer, but we're recently doing this on the Frontier, which is kind of the biggest, baddest GPU accelerated system that the US has to solve this problem. And it's available open source. So if you're interested, please go check it out in GitHub and you can get going on it. In the last maybe 2 seconds, I just want to also convince you of something that we've recently seen, that all of the scattering matrices that we've looked at, if instead of explicitly calculating them for every system, if we took all of the symmetry analysis we've done for the viscosity tensor and apply that to create scattering matrices, we would actually get within shouting distance of what you would get from doing all of those calculations ab initio. Okay, the process for how you create the scattering matrix, knowing something about the crystal symmetry and the conservation laws, is shown here. If I had infinite time, I'd convince you of it. But I'll just leave you with the results here, that if we created those same transport regime diagrams using scattering matrices that we had generated rather than explicitly calculated, again, this is something that folks who've done these large catalogs of topological materials are quite familiar with. So instead of explicitly calculating something for every system, if I could just do something with the symmetry, I can actually get within about 15% of what you'd expect from the fully ab initio calculated. So that's a mixed result in the sense that it turns out that microscopics matter, but microscopics matter as much as you can keep all of the symmetry information in your calculations. And then the transport calculation and the boundary conditions are really what dominates. With that, hopefully convinced you that there are systems which have hydrodynamic flow that go beyond graphene. Told you a little bit about how we think about the anomalous landscape for the various viscosity tensors. This is work that's really ongoing in my group, and I'd love to hear from the students here in the audience if you have some ideas around it. Then told you a little bit about Spartans, this method, and the scattering matrices that you can work with that may not require all the microscopics. So going forward, I'm really interested in these time-dependent flows, thinking about pre-turbulent regimes. There are recent results also from the Boltzmann group, and they're looking at more spatially complex hydrodynamic geometries. Like I said, the cross flows, looking at constrictions, those are all just a first pass of the types of geometries you'd want to construct. Sky's the limit here. And in fact, we and others are now introducing what we call the electronic Stokes theory, something that combines everything we've learned from the microscopic side as well as from the Stokes equation analysis. And the hope is eventually that all of these mathematician friends of mine will keep asking, well, how does this impact me? You keep using the word hydrodynamics, and they keep asking me about these energy cascades. Maybe we can actually help them out with their problem, and eventually maybe even start to use, instead of hard transport measurements, ways of doing computational imaging to get to these anisotropic fluids. Once again, I want to acknowledge the people who've done the work: George, Adam, Yashian, all the imaging from Uri Vul, who's now a group leader at Dresden, Asaf Hamo, who's a faculty member in Israel, of course, my colleague and friend Amir Yacobi, Claudia Felser, Ken Birch, and others. And thank you for your attention. Happy to take questions.
Thank you for this very nice talk. So, questions? I want to give you, yeah.
Okay, so maybe I had a couple of questions. One was like, in experiments, what do you need to do to get to the regime where electron interactions are much stronger than like impurity scattering or its effects and so on?
Right. Okay, so there are a few conditions that need to be satisfied. One, that the impurity scattering, particularly in this ultra clean limit, that mean free path needs to be really, really large. And that for us is meant single crystal samples, ones from Claudia, for example, and ones where the transport axis is really easy to identify for 3D systems in particular. The other set of constraints that we need to satisfy, of course, just an ultra clean sample won't get you there. There has to be a temperature regime where this either phonon mediated or the Coulomb mediated electron-electron interaction dominates over, say, the electron-phonon case. And that's something that we've been able to identify both ab initio and towards the end I was showing you how you could just glean that from a symmetry standpoint. There are some systems where that window is going to be large, and there are some systems where that window is going to be small. And perhaps the question you're asking is, how do I make that more pronounced over scenarios where that window is really small? And I think the answer to that is get as low symmetry as you can while still maintaining that very ultra clean limit. And then finally, of course, the types of geometries where you'd see these exotic fluid effects. So I think the channel flow is the hardest to say, hey, smoking gun hydrodynamics. Some of these cross flows or even these double bell geometries from the Weitzman group ought to be kind of where the field is going to go. Yeah. Hopefully I've addressed your question.
Yeah, and another question. So, I mean, in hydrodynamics, like even at the Euler level, you see a lot of interesting stuff like shock waves and so. I mean, so are there similar stuff people have seen just even at the Euler level?
Yeah, I think the shock wave component people have not yet seen experimentally in some of the systems that I talked about here. There are folks from the AMO side in their experiments where they have seen that. And in fact, there was it's really kind of interesting conversation I had with some of the AMO colleagues where they said, well, instead of making all these crystals, they can, of course, make a nice lattice of this and see some of the same effects. So they can see the shockwave physics. I just want to point out what makes doing this in condensed matter pretty cool is that you really have some of these other interactions that are competing that you can also tease out, which you wouldn't see in those scenarios. Yeah.
Other questions?
Hopelessly over time.
Maybe
So.
a very quick one connecting to
Go ahead.
nonlinear or turbulence. So yeah, connecting to nonlinear effects and turbulence. So can you make correspondences, or because under interactions, that's also another
Right.
interesting direction.
Yeah. So that's I mean that's really where we want to go with this these time-dependent flows is to get to some of the pre-turbulent regimes. I think we can get to pre-turbulent regimes that I can start to talk about truly nonlinear and eventually turbulent regimes. But so far, the experiments haven't really gotten there, and it's hard to see, again, from a theory standpoint, what geometries you'd make in order to get there. Yeah, without including that time dependence.
Yeah. Okay. Cool. Thank you. Thank you very much.
Yeah.